is Professor Smadar Naoz, who joins us from UCLA, where she's an assistant professor in the Department of Physics and Astronomy. So Professor Naoz earned her PhD in astronomy and astrophysics at the Tel Aviv University. She was next selected to be an IAU Gerber postdoctoral fellow with the Center for Interdisciplinary Exploration and Research in Astrophysics at Northwestern University. And she was then an Einstein Fellow with the Institute for Theory and Computation at Harvard-Smithsonian Center for Astrophysics before joining the faculty at UCLA. She's a world-leading expert in dynamic astrophysics and an excellent speaker, and we're very fortunate to have her here with us today, so please join me in welcoming her.
Hi, everyone. Thank you for having me, even if it's raining, or supposedly raining. So indeed, today, I am going to talk about, do you hear me well, like this?
Move it up a little bit.
Will do, like this. Is good? Right. So indeed, today I'm going to talk about gravitational waves in galactic nuclei and gravitational wave sources in galactic nuclei. And I think that in this room, we all agree that gravitational waves and their sources are really interesting. And I think, especially in light of LIGO's detections, which really transform the way that we sense the universe. So again, here, my next slide is kind of redundant because I think we're all in agreement that LIGO is awesome. And so I will keep at least the discussion about this slide very short. So what I'm showing here is the catalog of, an illustration of the catalog of the first cycle of LIGO and Virgo of binary black hole mergers. And they also observed one neutron star. Now, LIGO is still observing, as you all know, and they're detecting more and more. There's more and more detections of cool and interesting things. And in this talk, I'm going to focus mainly on black hole binaries, and I'm going to sprinkle around with some other interesting sources that I think are cool. So we want to understand how do we form binary black holes, and then how do we merge them? So we want to think about a recipe, right? The most convenient way for me to do that will be to take binary stars that we know are abundant in the universe, or at least in our galaxy, and I'll quantify it in a few minutes, and evolve them until they become black holes. So that's good. So let's think about this recipe. If I want a recipe, I need to have a cook. And here are my stars, and I want to involve them. However, when stars evolve and they get to middle age, you know, they expand, they lose some weight. This is what happens when we grow up. And the problem is that population synthesis tells us that for many of their systems, if I start with binary stars, one star, as it expands, engulfs the other one. And then at the end, we are actually ending up with one black hole. This is a very cartoonish way to explain a way more complicated situation. So this recipe has failed. In order to actually be able to get to binary black holes, I need to have the stars far away from each other. So when they expand and go through middle age, they really stay disconnected from one another, and we will get wide binary black holes. So that indeed works very well. The problem in this scenario is that when they are doing these calculations, they find that it's a little bit too much. Most of their systems are too wide, and when they're too wide, it takes them longer than a Hubble time to actually merge through gravitational wave emission. So in fact, it seems that what we need is a really fine-tuned part of this population synthesis of binary stars in order to get binaries, black hole binaries, that will merge within Hubble time, unless we can help them out. So here we have black hole binaries. If I can help a black holes to merge, that might be helpful. Will that help? So here I have the Muppets, two Muppets, helping black holes. So whoever heard my talks before, I really like to make jokes, and I do know that I'm really bad at telling jokes. So I warn you that there will be more of these. You're not obligated to laugh. It's okay, but just be warned. So we have these two Muppets. They are helping the black holes to merge. However, what I'm going to show is you don't need two, you actually need only one thing. So in this talk, what I'm going to argue is that supermassive black holes in the center of galaxies are really good in merging black holes. This is a natural place for binary mergers. And more than that, I will offer ways to disentangle between different sources that we see in the center of galaxies or everywhere else. So that will be the theme of this talk. So let's talk a little bit about supermassive black holes in the center of galaxies. So we know that almost every galaxy has at its center supermassive black hole with masses between million to a billion solar mass. And these supermassive black holes, they affect their environment, but surrounding them is also one of the most densest places in the universe called the nuclear star cluster. So if I have a supermassive black hole here and a binary here, I don't know if you can see this actually. Is there a stick? No stick.
There's a laser pointer in the top drawer.
Okay, thanks. Because my laser seems to about to die. So if I have a binary here, it will feel not only the gravitational perturbations from a supermassive black hole, but also the nearby stars and black holes and everything else there that will interrupt the binary to live. So you can tell me, fine, but why do we want to talk about binaries to begin with? Well, we do know that in our galaxy, most stars like to live in binaries. So here I'm showing the fraction of stars with companions as a function of the spectral type. So this is our sun. Our sun had 50-50 chance to have a companion, either happily or not happily, depending on your point of view. It did not. And but the stars that do create black holes, like these ones, most of them, if not all of them, are actually in binary configuration or higher multiples. So this is very encouraging. It seems that binaries are very pervasive in our galaxy. But you can tell me, well, you know what? These are binaries in the field or in clusters. Who told you that binaries or stars are forming in the same way in galactic nuclei as they are in clusters and the field? And this is a very valid question because we actually don't know. However, we do know one thing. We have a galactic center here in our own backyard. And very detailed observations on this galactic center can help us understand and disentangle what's going on in other places. So we can use them to infer and also to infer of what's happening in our galactic center in other galactic nuclei. But we also found all kinds of new puzzles. So I'm not going to talk about the puzzles. This is like a whole talk by itself. There are lots of cool things there. But I will infer from what we know on our own galactic center in other galactic nuclei, assuming that we're not special. And I know it's hard to think about that we're not special. So what did we learn? First of all, we already observed 3 binaries, 3 detected or confirmed binaries in the galactic center. And you can say, 3. Right. However, these are extremely complicated observations. And 3 are really awesome to observe in the galactic center. And we have 2 more candidates. And from these, they were able to put some estimates of what is the binary fraction that one would expect in the galactic center. And in fact, it seems comparable to massive clusters. This is very encouraging because, as I showed you before, in clusters, we have high abundance of binaries. So that is very encouraging. We also have some indirect evidence that binary are there. For example, we have X-ray binaries. So the keyword is binaries. These are either black holes or neutron star that accrete some either massive or less massive star, and we detect them in X-ray. We also have hypervelocity stars. So the idea of a hypervelocity star is that we have a stellar binary reaching to a supermassive black hole. It reaches too close, and the tides from the supermassive black hole break up this binary. One of them is being shot up very, very far away, and one of them is ending up in a very eccentric orbit around the supermassive black hole. And we have evidence for hypervelocity stars. And if this is the leading formation mechanism, then maybe indeed binaries are there all the time. And of course, we also have some observations of the disk properties seem to be only explained if you invoke binaries there. So we have all these indirect evidence, and we have some detections, and I would let Dr. Su say it better than me, that binaries are here and there, and binaries are everywhere. Okay, so now we know that the binaries can exist in the galactic center, and the question is, what is happening to this binary? So here is our galactic center, and here is a binary around the supermassive black hole. So the first thing that we can think that is happening is all the interactions with passing stars or other remnants that are there. And what happened is that basically this binary encounters so many things that meddle and interact with it until they're breaking it up and unbinding this binary. So whatever happens, we always need to take into account the fact that there are so many interactions that try to destroy our binary. And we can estimate this time scale of how long does it take to really destroy a binary. And we will use this time scale as an upper limit for our integration in everything that I'm going to present. Okay, let's go back to the binary once more. This binary can only be dynamically stable if these two are on a tighter orbit than their orbit around the supermassive black hole. Otherwise, it will actually do what the Yale process with the hypervelocity stars is doing, right? Only just for a bound system. So we need to make sure that they are hierarchy in scale. And what happened here, if I take these two, right, and they're orbiting their center of mass, and then the center of mass is orbiting the supermassive black hole, on short timescales, orbital timescales, nothing interesting is happening. This thing's just orbiting around, and it's practically boring. What I can do in that sense is to smash the mass around the orbit, meaning instead of treating this as three objects interacting with each other, I will treat this as two wires interacting with each other. This thing has been studied in the literature quite a bit. It's called the Kozai-Lidov. It was started actually with a Kozai-Lidov. We can write out a Hamiltonian for it. I'm not going to go over all the derivation of Hamiltonians, but I will point out some interesting things. So this term here, this represents the energy of the inner orbit. And the other term here represents the energy of the outer orbit. And now I'm treating this as two orbits. And the last term here that goes up to basically infinity, this is where I pushed all the interaction between the two wires that interact with one another. And this interaction term is here. So if I am smashing the mass around, this is called the secular approximation. If I'm smashing the mass around, then I can be fairly confident that this part remains constant, this part remains constant, meaning the two energies of the two orbits is constant, and everything that I'm describing comes from angular momentum exchange between the two orbits. As I said, this system was studied back in the 60s by Kozai and Lidov. And indeed, Kozai did this. He did an expansion. The expansion here is in the separation between the two orbits. And what he did is he truncated this expansion to the lowest order of approximation. Now, sometimes I like to give talks for a whole hour just about this because I find it really interesting. I will not do that. I will try to keep it extremely short here. I will just describe what Kozai and Lidov found. They have shown that from this system of Hamiltonian, and when you truncated it to the lowest order of approximation, Kozai found that the inner orbit eccentricity and inclination oscillates. Basically, I'm trading eccentricity for oscillation with this law that we found that is conserved. This law represents 1 minus e squared is the ellipticity, the eccentricity of the orbit. This describes to me the angular momentum, because if I have a radial orbit, right, angular eccentricity of 1, angular momentum of 0, and this cosine I describes the projection of the angular momentum over the total angular momentum. And he found that this thing is conserved, and then that there are some oscillations. When it's less inclined, it's more conserved, and it's more inclined, sorry, not more conserved, more eccentric. And it's more inclined, less eccentric, and vice versa. And we can see it here, basically this oscillation. More inclined, less eccentric, less inclined, more eccentric. What we have shown is that there is an inherent problem with this conservation law, and it's actually not conserved. This is the part where I can talk about for hours. And in fact, there is only, it's only conserved in a very peculiar part. Only if one of the members of my binary is a test particle, meaning no mass whatsoever, and if the orbit, the outer orbit, the orbit, for example, around the supermassive black hole, is axisymmetric. For example, if it's circular. Only in this case. So assume a test particle and a black hole and a circular orbit. Only then we can have this conservation law. However, every time that I have two black holes, this is already not okay. Every time that I have something eccentric, this is already not okay. So in our treatment, what we did, and we call it the eccentric Kozai-Lidov mechanism, because all the fun starts when the eccentricity is not zero, when the orbit is not circular. And we rederived everything. Everything is already changing already in the quadruple level of approximation. It's called the lowest level of approximation. And then we moved to the next level because it was funner. And basically, the business from all of this is that we can tap to way larger part of the parameter space. And the system is far more exciting and rich than thought of before. It's also very chaotic. So basically, it means that I can start from below 90 degrees and go above 90 degrees, something that I couldn't do before. Because this conservation law, I cannot change the inclination from below 90 degrees to above 90 degrees, because I cannot change the sign of the cosine if it's constant. If it's no longer constant, there is no problem. And for our case, it can reach extreme eccentricities. As extreme as 1. There are basically no problem to reach exactly 1 mathematically. Of course, what does it mean? It means that I can drive two things very, very close. Now, understanding how extreme they are, I want to show you an example. Here I'm showing the inclination. So how inclined the two orbits are with respect to one another. The eccentricity is 1 minus e, because I care about the pericenter passage, the closest approach, as a function of time. We can see here that there are these oscillations between inclination and eccentricity, just as Kozai predicted. But here we're below 90 degrees, here we're above 90 degrees and below, and here we get these very high eccentricity peaks. Just to drive this point home, this is what happened if I compare to the 60s calculation, the blue one. You can see that there is a qualitative difference between what the blue line thinks that the system is doing and what the system is actually doing. So we're going to use the red behavior. And the next thing that I want to draw your attention is to these very extreme eccentricity peaks. You can see that they are so extreme that it's, if I have just a black hole, two black holes in one AU, for example, these will reach, these will already collide and merge. So this is very interesting to understand how eccentric things can be. This was the job of three of my students. One is Gonzi Elish, is already an assistant professor in Georgia Tech. It's so funny when I think about her as my former student, but she was my former student. And then Ian, and they just grow up so quick. And then Ian and Jean, both of them worked with us when they were undergrads, and I was at Northwestern. And their job, Gonzi has looked at the test particle, but not circular orbit, and they looked beyond test particle. These are kind of complicated plots, so I will just go with this plot. Here we're plotting the eccentricity of the outer orbit as a function, it's cut off, of the function of the inclination between the two orbits. And the color represents how eccentric things have come in 1 minus e. So here we have this huge blob from the parameter space that shows that things numerically, which is numerical and we need to catch it in the moment, reached 0.99999. We're 6 nines in this, which means that it was pretty impressive given the accuracy of this. So we can have things extremely eccentric. So why is it good, right? If I have now a supermassive black hole, and it can induce extreme eccentricities for black holes. So here's my big guy, the supermassive black hole, and it merges, no Avengers fans here, okay? It's merging two black holes. There's one more Avenger reference, I guess. It's merging black holes, and everything is fine. So that was the work of, to understand this process was the job of another student of mine from UCLA, Baomin Hong. And in the first paper that we have done, we looked at soft binaries, so these binaries that form wide, just like population synthesis of stars would let us believe. And she included the eccentric Kozai-Lidov mechanism. She included general relativity of 1 p.m. and then 2.5 p.m. She also included the fact that we can unbind the binaries because of interaction with passing stars. Also the black hole, if you get too close to it, it can break up the binary. She included that too. And also Newtonian precession. Newtonian precession happens when we are very near a supermassive black hole and there is some mass enclosed and the outer orbits start to precess. We found that Newtonian precession, as we expected it, does not make any difference whatsoever. So let's see an example of what she did. Oh, before the example, apologies. I want to understand what are the timescales in the problem. So here I'm plotting timescale as a function of separation from supermassive black hole. It's some wide binary that we thought of. So there are different timescales here. This is the quadrupole. These are the Kozai timescale for oscillations. We can ignore the octupole. This is the general relativity precession of the inner orbit, just Mercury precession. Now, we have shown in previous works that if the general relativity precession is shorter than the Kozai precession, the eccentric Kozai-Lidov precession, we suppress eccentricity excitation. It makes a lot of sense because if that dominates, it basically decoupled from the supermassive black hole. So that gives me a place in the parameter space where the eccentric Kozai-Lidov no longer working very efficiently. It's over there, which is about 0.1 parsec. Here is the unbinding timescale, by the way, to show that we're very, very far away. There is one more timescale that I want to take into account. Dynamicists always think about what many body systems are doing. So I talked about this Newtonian precession, but there is a collective behavior of many stars and many stellar remnant that takes place in galactic nuclei, and it's called vector resonant relaxation. What it does, it's changing the inclination of an orbit. So a priori, it could have mattered a lot, right, because we care about the inclination of the system. But here, as you can see, that doesn't matter at all. So that is fine. So we worked inside of 0.1 parsec. I want to emphasize that beyond 0.1 parsec, people have found that the same behavior actually takes place. Just because of this resonant relaxation, it acts as our potential. So that's really neat. Okay, so here is an example that I promised of what Baomin did. Here's the inclination. This is 1 minus eccentricity. This is the semi-major axis of the inner binary. So I have binary black hole. Here, this is of the inner binary going around the supermassive black hole. So it feels the gravity. I show here the octupole in red and the quadrupole, the one that actually doesn't do anything. This is the 60s evolution, and the system did not merge. So this is just a sanity check to see that it's fine. Okay. Now, one of the things that we want to do is to calculate the black hole merger rate. However, there is a big danger of doing it. Because basically, if you take order of magnitude properties, you multiply them, you'll get an order of magnitude result, right? So there is always a danger in these type of works in multiplying just order of magnitude parameters. We will do that in what follows, just to see, are we in the ballpark, even to talk about this system to be interesting. So it's not to take we should not take this to the bank. We just want to see if we're using the same order of magnitude estimations as everyone else, do we get something that is relevant at all? So we're going to calculate the black hole merger rate from a system like this. So she ran a full Monte Carlo, and we want to understand what it gives us. So the merger rate can be estimated like this. The total merger rate is the number of galaxies that we have, the number densities of galaxies, time how many actually host supermassive black hole. We were extremely conservative here and assumed half. Basically, all of the systems should have a supermassive black hole, but fine. And then we have this rate here, and this rate is basically the number of binaries times the fraction of them that actually merged, times the rate that eccentric Kozai-Lidov merging them. So we can estimate these two from our simulations, and the cool thing that they are insensitive to how we're merging, how we're distributing those binaries around the supermassive black hole. And I want to devote a minute to talk about this, because I found that this is maybe counterintuitive. Because I just talked a lot about initial conditions and how we need to start the system, but then I say it's insensitive. So the thing is that my inner orbit, this thing, right, it has some distribution for how far it comes. It comes from population synthesis, and it has some distribution. And it also has some orientation, some inclination. Now, I can decide that I will put all my binary around the supermassive black hole in some crazy ring, because this is it. And then I can decide that everything is actually closer together, closer to the supermassive black hole. That means that the further away ring will pick up binaries that will actually be interesting with different separations than those that are closer by. So since this is a statistical exercise, there is no sensitivity to the actual initial conditions. Of course, that per system it does matter. So at the end of the day, this entire exercise boils down to how many binaries we have there, which is a big question, because we don't know how many binaries we have there a priori. So this was quantified here in this plot. This is the merger rate as a function of the number of binaries that are available for us to play with. And Baumin had different distributions. This to show what I just spent a minute to explain why it's insensitive to the distribution. She assumed a Bacol-Wolf. It's a very popular distribution to use. It basically assumed that, that we have an energy equilibrium in the center, and it's very cuspy. Or she assumed, let's say that we have a spherical distribution. If this is a real sphere, a real cluster, why not spherical? And as you can see, it really doesn't matter. The two lines really overlap one another. However, we can also say, maybe we can estimate the number of binaries that we have there. We know roughly what's the star formation rate in our galaxy, really roughly. And then if we assume that about 10% of everything is left as a binary black hole, what will we get then? And then we get between 1 to 14 gigaparsec cube to year. The reason of this 10%, because it's a popular thing that people just assume. I will quantify it in 3 slides better. But we can try to use that. Oh, actually, I'm quantifying it now, not in 3 slides. So to really quantify it, my other student, Alexander Stefan, went ahead and did the whole population synthesis, but this time including all the dynamical effects that I just mentioned. So he included the eccentric Kozai-Lidov, he included general relativity. He did not include gravitational wave emission, because that was something that Baumin did, and we already saw that it only depends on how many binaries we have. So we just want to understand how many binaries we have. And basically what it means is that we can start and follow binaries from birth to old age, even to death. And what we got, thank you for laughing. And what we got is that the black hole binary merger rate is about 20. Interestingly enough, we also got some interesting sources there. We found very exotic behaviors. We got lots of CVs, we got lots of Exery binaries, we got type 1a supernova that we predict that will take place in this region from double degenerate, so 2 white dwarfs. We did not get any single white dwarfs, which was interesting. We got also a neutron star black hole rate a merger rate of about 7, which maybe it relates, maybe it's not. We also, and we didn't get at all neutron star, which is also peculiar. So, if I'll just now go back to the exercise of calculating rates, and I'll take of black holes, I'll take this number, and I'll take also the lower bound that Baumin got. So we have between 1 to 20 gigaparsec cube per year. Now, this is for binaries here around the supermassive black hole, but because it's such a dense place, black holes can also meet each other and capture and merge. So that was done before, and that rate is estimated by 1.5. We can also think about going further away from the 0.1 parsec that I just claimed, and look at what happened if we have some asymmetry. So this is basically a derivative. For example, we have a bar in our galactic center, and that imposes symmetry even to smaller scales, and that can produce about between 0.5 to 15 gigaparsec cube per year. These all, by the way, use this 10% that I mentioned before. We can also think about the globular clusters. So it's a very popular mechanism to form binary black holes, merging binary black holes, and that is estimated between 5 to 50. So I told you order of magnitude, everything here is an order of magnitude estimation. So we always have an order of magnitude between them. All of this gives us between 8 to 86, which is actually not bad compared to the newest estimation between 9 to 100. So maybe this is in order of magnitude. We can explain everything using dynamical channels. I did not include here at all the isolated binaries. It's kind of doing injustice to the isolated binaries community, but okay. And all these stuff needs to be, again, taken with a grain of salt. It's interesting to see that in the galactic center, this plus that is actually taking a huge part of the parameter space. So gravitational wave sources in galactic nuclei seem to be very important. Okay. This is all nice, right? But we're not here to just play with order of magnitude things. What we actually want to understand is how can we make sense of it all, right? There's so many ideas and isolated binaries in the literature that try to explain how things form as they are, right? And we are seeing the end result. At the end of the day, what LIGO sees are all these mergers. So it's very similar of seeing the latest Avenger movie and trying to understand the origin story of each and every one of them without seeing anything. And it's really hard. So how do we do that? So one of the things that we can do is we can look for triple signatures, for example. So I will focus mostly on triples because why not? I only have, I think, half an hour left or 20 minutes left. So this is what I'll focus. But there are also other different signatures that we can try to understand from the different channels. So what do we get here? First of all, there is some preferred part of the parameter space. While I can sample different places, generally speaking, closer to the supermassive black hole is better. So that will be an interesting, because this is where the gravitational perturbations from the supermassive black hole is playing a role. Another thing is this inclination and eccentricity oscillations. So usually I don't show these movies because I find them very confusing, but this is actually what the Kozai-Lidov is doing in 3D. There are two different types of behavior that devotes a lot of happy explanations about resonances, which if anyone wants to ask me, I'll be talking for ages about this because I find it very exciting. But the point to show these two movies is to show that the 3D behavior is actually very rich. So if we can capture this richness, that will be very, very strong. So the first thing that Baumin showed that indeed we get that most of the systems that did merge are closer to the semi-major axis. So this is the number of systems that merge versus the separation from the supermassive black hole. What does it mean? It means that if I'm an observer here on Earth and I see something moving so close to the supermassive black hole, then the waveform that when it's coming away from me redshifted, compare when it's coming, this is coming away from me, this is coming to me, then it's blue shifted. And indeed, there were these studies that showed that this is detectable by LISA. And I had a LISA picture that disappeared. Okay. What else can we do? So we also have these eccentricity oscillations that I mentioned, and that was, which can be very, very powerful. And this is our latest paper, collaboration with Jess. And what we showed is that we can detect these eccentricity oscillations. So what I'm going to show you here is the awesome movie that my student Baumin did. Here I'm going to show the characteristic strain as a function of the frequency. This blue line is LISA sensitivity curve, so everything above is potentially observable with LISA. These oscillations as a function of time, of eccentricity, is basically blow up here. So this is eccentricity as a function of time. And we assume that LISA can see something so we're looking at window of 1 month, which is super short compared to all the other analyses. Fine. And this is at this galactic center, right? Because Alexander told us that there will be lots of binaries there in the galactic center. They just wait to merge. They're still not merging. It takes time to merge. So there's going to be so many of them. So let's go and see if we can see them. So in this movie, we're going to see how the evolution of the characteristic strain going in or moving back and forth inside the domain. So it corresponds, of course, with the different eccentricity snapshots. And these eccentricity snapshots we saw with Fisher matrix calculation that they actually, we can differentiate between each of any and every one of these. And this is how it looks. So this is what the system is doing as a function of time. This is the frequency as a function of time. These are these oscillations. And we're looking at only this peak right now, which is visible in LISA. And this is how it will look back and forth. And now you can tell me, okay, that's really nice. But what if you're wrong and there are no binaries whatsoever in the galactic center? Fine. There have to be binaries somewhere, right? So what if we'll go further away? We can go to 1 megaparsec. And this is the oscillation of some other system. And we're looking at larger timescales this time. And what I'm showing here is a more complicated system. This is a system for which the strain between 2 snapshots in LISA band are too close to one another to be differentiated using a Fisher matrix, for example. However, luckily, because the peak comes from the eccentricity evolution, because the peak takes place in different places, if I subtract between them both, I will have a very clear signal. So it's actually straightforward for LISA to run a template post 4 years of observations and look for these things. And we said, what if, as theorists, think as if we're LISA observers later on? And I'm sure we did not do the best job, but this is what we did. So we looked at the 1 minus eccentricity as a function of the semi-major axis of inner orbits, and we asked ourselves where in the parameter space I can see them in different signal to noise. So here we can focus on the yellow, which represents signal to noise larger than 10. And this is the part of the parameter space where EKL-driven eccentricity oscillations will appear. And that's very interesting because everything here is dominated by gravitational wave. The eccentricity is so high and the semi-major axis is so small that they're just in their way to merging. Still didn't merge, on their way. And here, these are things that are just there, just eccentric binaries that will be there. And here are things that LISA cannot resolve. We can also go to to further away. This is 1 megaparsec, and we have this differentiate in the parameter space. So not only we can differentiate between just binaries in the field that will undergo some gravitational wave emission and will merge, we can differentiate between different merging types in galactic nuclei, for example.
Sorry.
Yeah.
I don't understand. What are these distance scales at the top?
How far my binary is.
How far is from what?
for me. So from Earth, right? Lisa is here on Earth, or will be, not on Earth, but will be in space. And I'm asking how far the binary will be. And the binary will be, if it's 8 kiloparsec, so it's in the galactic center near the supermassive black hole. If it's in 1 megaparsec, in some other galaxy near some others.
I see. So the closest distance scale you're saying in our own galaxy.
Yes, yeah, this is in our own galaxy. But as Alexander showed, we expect high abundance of black hole binaries there. Okay, so remember this work that I mentioned. I mentioned briefly that we didn't get any neutron stars binaries there. And I want to very quickly explain what happens there. What happens to those neutron stars? So neutron stars, when they are born, they get a kick. And the kick is doing something to this binary. It's usually disrupt the binary. This was the work of Cicero Lu. She was actually doing this as an undergrad. And it's amazing work that she did as an undergrad. She did this paper. It's more of a thesis paper than anything else. It had lots of analytics and lots of numerics. It was really impressive. And she's now a grad student in Johns Hopkins. And let's say that this thing is going to become a neutron star. It's going to have some supernova kick. We know that supernova kicks happens in nature, so that is fun. And what happens is, when I have a supernova kick, there are different things that can take place. For example, I can unbind the binary, fine. I can unbind the triple and have a hypervelocity binary, or more interesting. I can merge the binary, which is interesting. I can just simply drive them into merger. We did not follow to see with Alexander how many of them will do that, but with Cicero, indeed, it seems that a substantial fraction will actually merge. And then my favorite one, we can fit the third body. So we actually throw a star or another member of the binary inside a supermassive black hole. So if what we throw inside is a star, we get a tidal disruption event. But if what we throw is a compact object, we get a gravitational wave event with Lisa. And both of them are very interesting. Both the tidal disruption event and the gravitational wave event, they have a precursor of a supernova before that. So I know it's hard to detect the supernova. I also talked about supernova type 1a inside galactic centers, and there's so much and so luminous, those places, that it's really hard to detect. But maybe I have faith. In the last, how much time I have? Like 5 minutes? I want to move to something slightly more exotic, which I'm very excited about. But it's the realm of more exotic things that usually we don't hear when we talk about gravitational waves. But I will talk about this anyways. So far, we talked about supermassive black holes at the heart of galaxies and binaries around them. But some galaxies have two hearts. And that makes sense from galaxy formation paradigm. Major galaxy merge, and as they merge, we can have supermassive black holes and supermassive black hole binaries. And they seem to stall around the sphere of influence. This is called the 1 parsec, the last parsec problem. Now, if I have my supermassive black hole binary, here it is, I can think about, and here comes the exotic part, the dark matter halo around this. So part of my work is also in cosmology and high redshift structure formation because it's fun. And I've been thinking a lot about dark matter around supermassive black holes. So a while back, together with Joe Silk, we thought, what if I have some dark matter halo, and I have some dark matter particles, and actually everything is being affected by Kozai and gravity. So if I have a particle here, it may become accreted on this little m1. So indeed, I can have this configuration where I have lots of things that will get accreted. So I basically, the Kozai is shooting everything inward, and I'm left with some configuration of a torus-like configuration of the dark matter profile. Fine. How does that relate to gravitational wave? Well, if the black hole is spinning, I have an ergosphere. Then I have a test particle that just spends its life or relatively speaking to us as an observer, spends its life on the ergosphere. And the accretion here is actually not symmetrical. There is some strange behavior, strange accumulation of dark matter particles on this ergosphere. So then we thought, is it high enough mass to become self-gravitating? And if it's self-gravitating, can we see a gravitational wave emission? And if, there's another if, and if we have self-gravitating thing that will undergo gravitational wave emission, before that, will we also have dark matter annihilation signal? Because dark matter may annihilate with one another, and we will get some high energy thing over there. So this is what we set to do actually last week. Well, it's not last week, but we finished it last week. And indeed we found that, yes, it can be self-gravitating. So we asked, what would be the density of a self-gravitating clump as a function of the supermassive black hole at the sphere, at the ergosphere, basically. So this is our min is our ergosphere. And this is this line. And then here, this red line describes what will be the self-gravitating clump, the density of a self-gravitating clump over a dynamical timescale, right? So dynamical timescale described to me what gravity is doing. This is why it's 1 over square root of g rho. So you can think about this as a timescale for collapse or a timescale for any significant behavior of self-gravitating clump. And we also included here the fact that something that dark matter maybe can annihilate. So that includes annihilation. That does not include this annihilation. We don't really know if dark matter annihilates or not. It may be. So that looks very promising. The next thing that we wanted to understand is what is the accumulated mass. So here I'm showing the accumulated mass as a function of time. And this we can just take from our simulations. So I can estimate the different mass that I will have in this halo as a, just because we know something about cosmology. And it will be different for each of the supermassive black hole because we are using the M sigma relation. Each supermassive black hole represents a different halo. So we can estimate that. And as a function of time, we get these type of curves that the color code is the smallest halo, the smallest black hole and the biggest black hole. This time scale is sensitive to the Kozai time scale. This is under some assumptions of what Kozai is what is the system configuration is. But this is really interesting because look at the masses. These are huge masses that are being accumulated as a function of time on the ergosphere. And for a long time scale, we get this accumulation. So we can ask ourselves, what are the different time scales that are relevant in this system as a function of this supermassive black hole mass? So here I'm showing the gravitational wave timescale. So this is to merge a point mass, which is not true to think about, but this is the best that we can do right now, with another point mass. So the clump, the dark matter clump with the supermassive black hole, and that is longer than the time that it gets to annihilate. That's good. That means that I'm not merging the dark matter clump with a supermassive black hole, but I can annihilate them as I'm accumulating more and more. At least for 10 to the 8 years, this happens. So finally, and I warned you that this is exotic. Finally, we can estimate what will be the dark matter gravitational wave that may accompany with some dark matter annihilation signal. So it will be detectable by LISA, and it may have a signal of dark matter annihilation. So it is exotic, but it's also really fun, at least for me, to think about. And it also gives two different detections. So in the multi-messenger astronomy, I think this is really strong. And it's a signature for black hole binaries on the parsec level, which is something that supermassive black hole binaries, which is something that is really hard to detect. So just to finish the job here, what I showed you is that the heart of galaxies are really awesome. They're a natural place to a lot of, this actually does beating, so I'm sorry if it distracts. It's a wonderful place for different black hole mergers and other gravitational wave sources. And I showed you that we're starting to have the tools to differentiate between different sources. And that's it. Thank you so much.